Hydraulic pressure performs a variety of tasks in an aircraft, including but not limited to the extension and retraction of the landing gears, flaps, moving primary flight controls, in some models closing or opening the main cargo doors, and plenty of other tasks. If for any reason we could not use the hydraulic pressure, then we might use the large and heavy weighted electric motors and several electric generators to generate as necessary electric power to be used by those motors and operate such important flight controls for us. Mainly and in an aircraft, the hydraulic pressure is provided by the hydraulic pumps. Generally, we have two types of hydraulic pumps in an aircraft. We have engine-driven hydraulic pumps, and then we have electric hydraulic pumps. The engine-driven hydraulic pumps are connected in the accessory gearbox of the engine, and in jet engines the accessory gearbox is located in the bottom of the engine, and then we have a tower shaft which is connected between the accessory gearbox and the compressor of the engine. So once the engine is operating, rotation of the compressor will be transmitted to the accessory gearbox via the tower shaft, and then the gearbox will rotate, and all the units which are connected in the gearbox will receive their rotation, and one of the units is the hydraulic pump. So the hydraulic pump which is connected in the accessory gearbox of the engine, it is continuously connected there, so we do not have any controls over that pump, and we cannot disconnect it during the flight. The only control that we can have over an engine-driven hydraulic pump is via a switch which is located in the overhead panel of the cockpit. Once we place the switch to the off position, we energize a solenoid. So once the solenoid is energized, it routes the output pressure of the pump back to the reservoir, and in this case the pump will be depressurized. As long as the pump is still connected in the gearbox, it is rotating, and because the engine is operating, and but the output pressure will not be fed to the system. But for the electric hydraulic pumps, we are acting like we turning on or off a bulb or a lamp, for example. So once we place the electric hydraulic pump switch to the off position in the cockpit, in fact, we turn off the electric motors, and once the motor is turned off, the hydraulic pump will be stopped and the output pressure will be blocked, in fact, so the pump is going to be off. So as part of the before taxi procedure, mainly in Boeing 737 Classics, we turn on both electric hydraulic pump switches once the engines are running. So we have 4 pumps available to provide us output pressure both for system A and for system B. The question is that let's say we are in a cruise flight, in a stabilized flight, and we are not operating any flight controls, we are not extending or retracting the landing gears, we are not extending or retracting the flaps, but as long as all pumps are operating and producing as output pressure, where does the pressure go? Because as a general understanding, once a unit is operated in the system, so system pressure will drop, and the pump is there to provide back this pressure to the system and keep it up to the limit, which is around 2800 psi or up to 3000 psi. But once we are in a cruising flight, or maybe on the ground, let's say for example, and all pumps are operating and producing as output pressure, so where does the pressure go? We are not operating any system. If you ask this question from most of the flying crew, the answer will be that we have a relief valve in the system, and the relief valve will open and return back the excess pressure to the reservoir, and the relief valve will help to keep the system pressure to 2800 or 3000 psi, whichever the system is designed for. But this is not the proper answer for this question. So what is the proper answer? To find out the proper answer, we need to take an hydraulic pump and put it on the table and open all the fasteners, screws, bolts, everything, and look inside and see what inside is, because everything is inside of the pump. Because of this, I'm calling it a Meson pump. The difference between this pump and other pumps in the aircraft is that an hydraulic pump in an aircraft is a pressure compensated pump. So in very simple words, in simple way, let's find out and explain what inside is and how an hydraulic pump works. Generally, we have different types of hydraulic pumps, and the most famous and in use types are the gear type and the piston type pumps. In most general aviation and transport category airplanes, piston type pumps are used. The two most common types of the piston type hydraulic pumps are the bend type and linear axial type. Between the two types mentioned already, the most common type in use and very efficient is the linear axial flow piston type pump. In this type, a shaft is extending out from the pump, which is connected to the engine gearbox and receives rotation from the gearbox while the engine is running. Or in case of the electric pump, the shaft is connected to an electric motor. The motor is either powered by DC direct current or alternate AC current from one of the AC electric buses. Inside of the pump, some number of the pistons are connected around a separate shaft. The shaft is attached to a swash plate which is placed in an angle, and the pistons rest at the front face of the swash plate, and based on the output pressure, the size and number of the pistons differ from one pump type to another. Because of the angle, as the pistons rotate, they receive different in and out movements. For example, when a piston moves from the high angle part of the swash plate to the lower angle part, it starts to suck the hydraulic fluid, which has been supplied via the inlet line and in the intake chamber of the pump. As the same piston moves to the higher angle part of the swash plate, the angle causes the piston to have an outward motion inside of its cylinder, and this action will cause the hydraulic fluid to enter to the output chamber of the pump with higher pressure, and the hydraulic fluid will move out from the pump. The process continues till the system pressure in the outlet line of the pump reaches to predetermined limit, for example 3000 psi. There is a small chamber inside of the pump which is incorporated with a spring-loaded shaft. The shaft is attached to the back face of the swash plate, and the chamber receives the pump output pressure via a line connected to the outlet line of the pump. As long as the system pressure is below the predetermined limit, the piston is forced by the spring tension to keep the swash plate in a maximum angle. As much as the system pressure reaches to the maximum limit, the output pressure is also fed to the chamber, which acts against the spring tension and causes the small piston to move backwards. Moving the piston backwards will move the swash plate the lesser and lesser angles, and once the system pressure reaches to its maximum limit, the swash plate is driven to the zero angle. Since the pistons have contact with the swash plate, they will also move to the zero angle position. Now the pump still moves, but the pistons will not have in and out movements inside of their cylinders, and there will not be any sucking and pumping activity. Once we operate an hydraulic unit such as gears, flaps, or any other flight controls, obviously system pressure will drop. Drop in the system pressure will cause the piston and the pressure compensated chamber to move out against the spring tension and force, and will change the zero angle of the swash plate. Once the swash plate is angled, it will move the pistons from the linear position, and same as before, the sucking and pumping function of the pistons will start and output the hydraulic fluid under positive pressure via the output line of the pump. The process continues back and forth. So as we explained the internal structure of an hydraulic pump, as a summary, we found out that we have some number of the pistons which are connected around a shaft. So once the shaft is rotating, the pistons will also rotate. They will have a linear movement, but at the front face of a swash plate, the pistons have connections here. So as much as the swash plate is angled, for example, when the system pressure drops, then the swash plate will have an angle. So this angle will cause the linear motion of the pistons inside of the cylinder, which are inside of the pump. So what happens now, there will be output pressure from the pump. But once the system pressure reaches to 2800 psi, or let's say to 3000 psi, and there will not be any need for the pumps to produce output pressure, so what happens, the swash plate will come to zero angle. Once it comes to the zero angle, since the pistons have connection with the swash plate, they will also have zero angles. Now the pump is rotating. The pump has connection with the engine gearbox, or let's say the pump has connection with the electric motor, but since there is not any angle inside to the pistons will not have any sucking and pumping activity, so the output pressure of the pump will come to zero. This is the main function of the hydraulic pumps internal, in fact. But same as other units of the aircraft, we might have some internal malfunction with the hydraulic pumps. This internal malfunction does not mean that the hydraulic pumps will break down completely, no, but maybe there will be some problem with the swash plate and it will not angle itself once the system pressure drops. So what happens now? In this case, the pump will continuously produce output pressure as long as we do not need this pressure. So the system pressure will move from 2800, let's say, to 3000, then from 3000 psi it will move to 3500 psi. At this point, the relief valve will start its function, and the relief valve will open and will route back the exhaust pressure to the reservoir and keep the system pressure to its limit, to what limit it is designed. We do not have any indications in the cockpit. We don't have any lights. We don't have any other indications to indicate for the pilots that for example, associated pump has got internal malfunction. So how the engineers or the mechanics or technicians can find it out? Once they perform their normal task, or for example, the checks or the any type of other, for example, routine checks that they have on the aircraft, they find out that the relief valve has relieved the system pressure, because we have an indication there. Once the relief valve relieves the system pressure, so there will be some indications for the engineers. So at the top of the relief valve, there will be a small red lever. The red lever will come out. So this will be an indication that the relief valve has relieved excess pressure in the system. What does it mean? This means for the engineers that maybe one of the hydraulic pump has got internal malfunction and the pump could not adjust its angle to, for example, bring the system pressure or to keep the system pressure to its limit. System pressure went up and up, or high and high, and then the relief valve relieved the excess pressure. So what they do, they based on the checklist and procedure that they have, they will find out which pump has the malfunction. They will replace the pump to a new one. So thanks, colleagues, for watching the video. That was a very short and rough presentation regarding the hydraulic pumps, how they are functioning, and please leave your any questions that if you have in the comment box of this video. And my next presentation will be regarding the other hydraulic units and valves and used in an aircraft, and please follow my next presentation as well. Thank you very much, and see you back in my next presentations.